Alrighty. Welcome back to everybody who's here with lecture. Hello again to everybody who's tuning in after the stream, but watching. Okay, Carenza, you have several questions. Let's see. Show us a problem with chemical reaction given the liters of both reactants and the concentration of a product. Okay. Asking for a coefficient, how many grams of product were produced. So there's one of the react. Yep, we totally can. So, for instance, I can totally cook up a problem to that effect. Prathana. Okay, and then Kate, you've got a chapter 10 question. Kate, here's the beautiful thing. So there are rules for sig figs with logarithms. So you don't have to worry about sig figs with pH. There are rules for applying sig figs with pH, but it's something that honestly I don't cover. I don't even teach it in Chem 400. I do teach it in Chem 401. Sorry, this is a little right. There we go. But you don't need to worry about it for now. And all of the pH questions on the final will be multiple choice, and all options will have the same sig figs. So you only have to worry about determining the correct value. Okay, Esther, we can totally hit up your Lab 11 question, and we actually have an email question about Lab 11. But first, let's go ahead and hit up this Carenza and Prathana actually both have questions about... oh wait, this is the lecture. Let me open the office hours slide. That's the lecture stream. There we go. Okay, so let's do a problem like the following. Okay. So, let's see here. .0 milliliters of we'll make this aqueous hydrofluoric acid are mixed with 42.0 milliliters of calcium hydroxide. There we go. This reaction produces liquid water and and aqueous salt. All right. Let's see. I'm just reminding myself of what you're asking. Okay. The molarity of the salt solution was 0.208 molar. All right, and then step number 1 is what is the stoichiometric coefficient of water in the balanced chemical equation. Number 2, oops. How many grams of aqueous salt were produced right, or were made, and then 3, let's see. Aqueous salt were made, and then finally, if hydrofluoric acid was the limiting reagent, or limiting reactant, how many grams of it were consumed? Oh, Esther. Sorry, I just now saw your Yep. Yep, we can totally look at some chapter 10 stuff, Brianna. I'm just now seeing these. Esther, I believe I've totally forgotten to, or I've forgotten up to this point, assign practice problems. Okay, Krenza, you are welcome. You are absolutely welcome. I will get the Chapter 10 practice problems up. I've just been super focused on exam writing that it skipped my mind that I haven't given problems from the back of the book. In general, the all the Chapter 10 problems are pretty darn good. There's my pencil. Sorry, dipping down. But I will upload those to Canvas around or by the end of our live stream here, probably a little bit after, just because I have a feeling it's going to be a hop in time. Okay, let me open up some biz. Okay, so I'm gonna, whoops, I did not mean to delete all of that. So I know that this problem type, some people wanted to see it worked out, and I totally will work this problem. But I want to just give a couple pointers to maybe like places to start. So I'm gonna white out part of this. Whoops. All right. So let me hook you up with some starting points. Maybe you can take a crack at this, and I can circle back as I answer some other things up here. But here are some starters. Obviously, this guy right here, we've just got to balance. All right, which is something hopefully we can do. Now, here with number 2, oops. With number 2, kind of my starting hint is we've got our molarity of salt, right? Which is moles of it over liters. These liters right here, this is the volume of the 2 solutions mixed together. And then finally, kind of my hint for number 3 is take the grams of HF. Oh, sorry, not grams of HF. Take the grams of salt from step number 2 and use stoichiometry. Those are my starters. So those are kind of like my hints for, those are some places to start. I'll circle back. I will circle back around and work this problem in its full glory, and this is the problem I'm talking about. But hopefully that gives you a place to start with, and I will dive into, let's see, the next question, I believe, was okay, Kate, I answered that. Esther, okay, lab 11. Oh wait, hang on. I don't know if you've read the lab page that said, "Be sure you have the updated one." I literally just opened opened up the one that's not updated. So let me grab the revised version. Okay. Okay. So, okay, so, Esther, Lab 11, can you show how to set up number 9? Oh, wait, hang on. Oh, you had number 6, actually, first. Number 6, okay. On page 4, it's page 3, page 4. Use the information displayed in the simulation to write down the concentration of hydronium and hydroxide ions in the chicken soup before the water was added. That's awesome. Based on these concentration values. Oh, okay. Let me just pull up the video. I remember, I feel like they do this using a pH meter, but give me a second. Okay. Oh, hang on. pH of household products. All right, hang on. Sorry, I'm trying to find where there's a chicken soup part. Let's see. Here, hang on one sec.
Cabbage water, I'll just take purple cabbage and put it in some water or purchase buffer at pH 1 and 11. Now let me just take samples, which are on my clear, and try to estimate what the so the idea.
Oh, in the... I might be looking at the wrong thing. Oh, I'm looking at the Susan. Okay. Awesome, thank you. I was looking at the lab video. Okay. Here we go. Simulation time. Okay. Oh, okay. So here, okay. Dude, thank you. I was like, I was scrubbing through that video being like, I don't see any chicken soup. Okay. Let's take a look at this. So Esther, this is your question. Number 4 was the first one you asked for, right? Lab 11, number 6 on page 4. Okay, sorry, the chicken soup was number 4. Spit contains compounds such as enzymes and ions that aid in the digestion of foods. Based on the pH of spit, predict the likely acid-base percentage of the major ions present in spit. Isn't this a lovely conversation? Okay, sorry, that's chicken soup. Let's empty my chicken soup out of here. Where is spit? Okay, sweet. We got spit. Okay. All right. Now I can actually answer this. Okay, let's take a look. So this is. All right, so this is lab 11. Question 6, which asks us basically to predict whether the major, essentially, we're having to predict whether the ions, or I should say the compounds in saliva or spit is are whether these compounds are acidic or basic. Right, and so when you look at this simulation, we see that spit has a pH of 7.40, and the thing to remember, whenever you're dealing with the acidity or basicity of a solution, the magic number you want to remember is 7. pH 7 means that you are neutral. All right, this is the Zen mode. This is neither acidic, neither acidic or basic. It's neutral. This is your Switzerland. If I don't know why I wrote PL, if your pH is less than 7, this means your solution is acidic. And if your pH is greater than 7, it's the ugliest greater than I've ever written. pH greater than 7 means that your solution is basic. All right, so the fact that this pH is, I mean, it's close to 7. This is pretty darn near neutral, but it is above 7, so this solution is slightly basic. So apparently, our saliva is slightly basic, and so that would lead us to indicate that the compounds, the enzymes, and whatnot in our saliva are probably basic because the pH is slightly basic. So that is, excuse me, hiccups. Lab 11, question 6. I don't mean to like hop, skip, or jump over anybody necessarily, but I've seen a couple other Lab 11 questions. So I figure there's another one on number 9. So I'm going to go ahead and answer it while we're kind of rolling on the Lab 11 content. Oh, wow. Based on the pH, so this is more spit. And then I'll circle back around and get to everybody, but it seems related. Based on the pH and pKa of spit, and that spit contains 0.0250 molar bicarbonate, what is the concentration of carbonic acid in spit? Okay, this is a great question. This is a hidden question about the David Hasselhoff equation. The Henderson-Hasselback equation. The Henderson-Hasselback equation is an equation that allows us to calculate the pH of a buffered solution. So the equation is pH is equal to pKa plus the logarithm of the molarity of A minus over the molarity of the weak acid. All right, so this is the Henderson-Hasselback equation. And the in this problem, you'll notice, so they're asking us to find something very specific. So they're asking us to find the concentration of carbonic acid in spit. Yes, I totally could. And you know it's awesome. Okay, it's connected to this as well, Esther. So it's kind of, we'll hit all these birds. I don't know how many stones it'll take, but we can do it. So we're asked to find the molarity of HA, and look at what we're given. So HA, I should, to be more specific, HA or carbonic acid is H2CO3. All right, and we're given our pH. We know the pH from actually number 6, which we just did. 7.40 is the pH of spit. They give us the concentration of A minus, right, which is actually the concentration of bicarbonate, which they tell us in the problem, right, is 0.0250 molar. So looking at the Henderson-Hasselbach equation, we've got our pH, we've got our A minus. They want us to find our HA. So we just need the pKa. And in part 8A, they ask us to look up the pKa of carbonic acid. So I know it's around 4.7-ish, I think. But let's see. Oh, oh, really? It's a little higher. pKa of carbonic acid when you look it up, or lower, I should say. No, higher. pKa is, I thought it was 4.7. It's 6.35. I'm glad I looked it up, because now we have this, and now we just have to solve for the denominator of our logarithm. Now this will require us to kind of flex our algebraic prowess a little bit, but we can get there. So we have pH. Let's do some algebra. We've got pH is equal to pKa plus the logarithm of carbonate, or no, carbonate, bicarbonate, over the concentration of carbonic acid, which is what we want to solve for. All right, step number 1. Gave you a pH for what is so the first thing we could do is subtract. Sorry. Oh, okay. Gave you. Really? Okay, here, hang on. Oh, not. Oh, okay, sorry. Now I'm totally tracking with you. Let me double check my numbers. I may have totally gotten this wrong. Oh. Okay. All right, Susan. I'm super glad you brought this up, because turns out yeah. No, Susan, you're spot on. So it turns out, and this is why I'm glad you brought this up, because I see, Esther, you got a pKa that's like around what mine is. So I double checked my source, and it turns out that carbonic acid has 2 pKa's because there's 2 protons on it, right? There's 2 H's that I can donate, and 6.35 is the pKa for its second proton, but the first proton, and that's the one that is used in this reaction, has a pKa of what was that number? That was like 3.6 something. 3.49. There we go. So that is the value that you want to use for this calculation, 3.49. I just grabbed the first pKa that I saw, but turns out that there are 2 different pKa's for carbonic acid, and the correct one for this calculation is the 3.49. All right, so when you subtract pKa from both sides of this equation, you get pH minus P. Oops, hang on. Don't actually want to do this here. Yeah, totally. Totally, but I'm so glad you brought it up because it gives everybody an opportunity to get on the same page. Okay, so we've got pH minus pKa is equal to the log of the concentration of bicarbonate, molarity of bicarbonate over the molarity of carbonic acid. All right, now we actually have values for both of these, so let's go ahead and plug them in. So our pH is 7.40 minus our pKa, which is 3.49. So 7.4 minus 3.49. So this comes out to be 3.91 is equal to the logarithm of, and I'm just going to go ahead and plug this in right now as well. We know what the molarity is in the numerator, right? It is a 0.0250 molar over the molarity of carbonic acid, which is what we're trying to solve for. All right, now, so as of right now, I'm gonna clear the stage for just a second, or this mini stage on which I'm working this problem. So now we're in not a pickle per se, but we need to remember how to jailbreak something from the argument of a logarithm. Actually, so this is something that I just want to write out because this is probably something that most of us don't just remember off the top of our heads from the last time we took algebra. So you need to recall a property of logarithms. Let's say if you write an expression, 10 to the power of log 4. The answer will be whatever is inside your argument. 10 to the power of log 4 equals 4. Or 10 to the power of log x, because whatever this is in the argument, when you raise 10 to the power of log of that thing, it will equal that thing. Okay, so that's one thing we need to remember. The second thing you need to remember is if you have an equation. All right, so let's make room for our second thing. Let's say we have an equation 4 is equal to 2 plus 2. We all agree that this is true, right? You can take both sides of this equation and make them exponents of 10. You can write an equation that says 10 to the 4th is equal to, is equal to 10 to the 2 plus 2, and it's still true, right? Because this 10 to the 2 plus 2 is just 10 to the 4th. They're the same no matter what. And you want to keep these two properties in mind as we go to solve this last part of the problem. Because right now, we have an equation that says 3.91 is equal to the log of 2.0250 molar over the molarity of carbonic acid. All right, first, I'm going to make both sides exponents of 10. All right? I'm going to make both sides exponents of 10. When I do, oops. When I do, I'll have 10 to the 3.91 is equal to 10 to the power of log 0.0250 molar over the molarity of carbonic acid. All right, that's what I've done. I've made both sides a power of 10. We can see here that when you do that to an equation, it's still true before and after. So I've done that here. The question is why? The answer is on this side of the equation. Whenever you have here 10 to the power of log x, the answer is whatever's inside the parentheses. So this side is just equal to 2 or 0.0250 molar over the concentration of carbonic acid, and that's equal to 10 to the 3.91. All right, we can use our calculators to determine what 10 to the power of 3.91 is, using that 10 to the x button. So this is 8,030. Don't really worry about sig figs for these exponential problems. Now we have to solve for our concentration of carbonic acid. All right, so we get the concentration of carbonic acid times 8,130 is equal to 0.0250 molar, and then you divide by 8130, and that will get you our answer. All right. So just there we go. So finally we get our concentration of carbonic acid is equal to 0.0250 molar divided by 8130. So 0.0250 divided by 8,130. Whoa, is a crazy small number. It equals, let's see, 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5, 308 molar. Or you could write this in scientific notation if you wanted to. This would be times 10 to the negative 1, 2, 3, 4, 5, 6. All right, so that is how you solve that problem. Also, a good this is a good one to do altogether. It's acid-base review, right? It's buffers, it's pH. Esther, I know you had a question on. Okay, this will also be good review. Good chapter 10 review. So here's lab 11, question 8C. I'm thinking I might set up the prompt for this. They ask us to draw the reaction showing the bicarbonate buffer system reacting to number 1 acid and number 2 base. All right, so the first, here's the buffer. Every buffer system involves a weak acid. Oops. Here we go. A weak acid, HA, and its conjugate base. So we form H3O plus and A minus. All right, and for the carbonic acid system we've been talking about, HA is H2CO3 plus water. Yep. We totally can. And the cool thing is this problem that we're doing, Susan, will totally give us reps with that, and then we can totally do problem 1 as well. So, oh my gosh. I was talking muted this entire time. Holy moly. I apologize. You guys haven't been able to hear a word I said. My mic was muted. Okay, I'm so sorry. So anyways, this will give us reps doing that. And then we'll do number 1. Oh, I wasn't? Oh! Well, thank goodness. I almost said thank goodness. But also that means my mic mute doesn't work. Oh, fortunately I don't mute it and swear or anything, otherwise that would be rather embarrassing. Like Ron Burgundy in Anchorman. When he tells San Diego to go do something. Okay. If you've never seen Anchorman, go watch it. Okay, I'm so glad, Brianna. I'm so glad. I'm like relieved. I was like, oh my gosh, was I just like, how did they know what I was? Because we've been chatting in the chat. I was like, either you guys are telepathic, which means you know what I'm thinking, which terrifying in its own right. I'm glad it was working. Okay, so here's the reaction, right? Here, the HA is carbonic acid, right? And the A minus conjugate base is that carbonate ion. And when you add acid, that means they want you to write the reaction between the conjugate base and hydronium. And when they tell you to add base, sorry, I need to switch the colors of these arrows. Adding acid means that we're going to react our conjugate base with hydronium. When they ask you to add base, that means that you are going to react your weak acid with hydroxide. All right. So when in this problem, when they ask you to draw the reaction showing the bicarbonate buffer system reacting to acid and base, when you add acid, it will react with your conjugate base, right? Because acids and bases like to hang. And then when you add base, your base will react with your weak acid because, again, acids and bases like to hang. So these are the two reactions we need to draw. First, let's do adding acid. So we start with our conjugate base plus, and this is aqueous, plus adding acid means adding hydronium, H3O plus. These two react. Okay, so remember what an acid is. Acid is an H plus donor. And remember what a base is. Base is an H plus acceptor. All right. So if carbonic acid is going to, well, or if hydronium is going to donate an H plus, that means that it is going to lose one hydrogen and it's going to lose a plus charge. So it will simply become H2O. If bicarbonate is going to accept a proton, that means that its hydrogen count will increase by 1. So it'll be H2CO3, and it's got a negative charge. When you add a positive, you get a neutral compound, so there's no cationic charge for carbonic acid. So this is the reaction using the Bronsted-Lowry acid-base definitions. This is the reaction that will occur when you add acid to this buffered solution. Now let's write the one where we add base. When you add base, your weak acid in your buffer solution, carbonic acid, is going to react with hydroxide. All right, now again, this is our acid, carbonic acid, and hydroxide is our base. I've already written up the definitions of each there. When your base accepts a proton, its hydrogen count will increase by 1. So instead of having 1 hydrogen, it'll have 2. Hydroxide will become H2O. Also, it gains a plus charge, which will cancel the negative charge it has. Now, the acid is going to donate a proton. That means its hydrogen count will decrease by 1. CO3, and it lost a positive charge, which means there is a negative charge left behind. So these are the two reactions that happen. The first when you add acid to this buffered solution, the second when you add base to this buffered solution, and we got our products, our answers, by using the Bronsted-Lowry definitions for acids and for bases. All right, Susan, you wanted to see number 1 on this lab. Let's take a look. All right, when solvent, water, is added to coffee to dilute it, did the water act as an acid or a base? Explain your answer in 2 sentences, then draw a general chemical reaction for the reaction of water with a Bronsted acid. All right. Yes. So a Bronsted acid is a proton donor, H plus donor. All right, that's what it is. And so a Bronsted acid is a proton donor, and the generic way to write a Bronsted acid, because that's kind of what they ask for, is just HA. So HA is a generic Bronsted acid. Now, when a Bronsted acid reacts with water, you're going to have HA, and all our acids are aqueous. Reacting with water, H2O. Now, to figure out our products, we need to know what our things are doing. Now, this, HA, is our acid, and that means that water must be our base. Bases, Bronsted bases, are H plus acceptors. Bronsted acids are H plus donors. Right, H plus acceptors, H plus donors. Now, we're going to do the same thing that we did in actually the previous part of this problem, so this is good repetition. A base, when it donates a proton, is going to lose one of its H's, right? So instead of having 2 hydrogens, it'll only have 1. It also... Oh! Say, that is a great question. Okay, so we've lost a hydrogen. We've also lost a positive charge. That is going to leave a charge of -1 behind after that base donates a proton. All right? When you look at your acid, Wait. Oh my gosh. I'm so sorry. I am so sorry. Hang on. My dyslexia flipped those around. I apologize for everybody who was like, all of a sudden thought you were getting this and now you're crippled with doubt. Let's think about this. Water is the base in this reaction, right? It is the base. Bases accept protons. That means that its hydrogen count needs to increase, not decrease. Not only does it accept a hydrogen, it accepts a hydrogen with that positive charge. So H2O will turn into hydronium, H3O+. Now, because HA is the proton donor, it loses H+, leaving behind simply A, and because it lost a positive charge, minus charge is left behind it. All right, so this is say you are welcome. So this was lab 11 question number 1. Buffer reaction. Would the buffer reaction from 2 slides ago be the acid-base neutralization that produces bicarbonates? Lab 11, question 7. Let me take a look. They really were into spit when they wrote this lab. Let's see. Can I ask if I can say the problems and their response that you type? Oh! Okay, sorry. Yes, Jen. Sorry. Yeah, I don't know why that's never crossed my mind before. Before. Totally. I'm sure it can be bewildering. And I'm like, oh, great question. And you're like, I'm looking at the chat. There's like 8 questions in there. I'm sorry. I will try to be more specific as I answer them. I can imagine that would be confusing. Okay, Esther. So a buffer reaction from 2 slides ago. Oh, you're saying one of these guys. I think they're going to be close. Close, but no, not quite a cigar. Oops, sorry. So if you look, and you'll see, they're very similar, but they're slightly different. So this is lab 11, question 7. Okay. Lab 11, question 7. They ask you to write an acid-base neutralization. All right, so already when we see that word neutralization, we're talking about some acid, HA, plus a metal hydroxide base that's going to produce water plus a salt. And a salt is a cation and anion. And the salt will be made up of the metal cation plus A minus. And they tell us in this problem, they tell us that the identity of A minus needs to be bicarbonate. All right, so if A minus is bicarbonate, then HA has to have the same formula, just one more hydrogen attached to it, right? So we've got A minus and HA. We just need a metal that will be soluble in water when combined with bicarbonate. Now, you may be going, solubility rules, we didn't learn anything about bicarbonate. True. Since we didn't learn anything, we should pick a metal from the always soluble list, right? The always soluble list. So, potassium's a great one. Not the only answer. You could do potassium, you could do sodium, you could do ammonium. There's tons of things on the always soluble list. Any one of them will be correct. So the neutralization reaction then would be carbonic acid, H2CO3, aqueous, plus, I'm going to use potassium because I think it's cool, because KOH has a KO in it. These two react to produce water, which is a liquid, plus, now the salt is KHCO3, and that's aqueous. So this is one possible answer for the neutralization. Really, any answer is acceptable as long as you use the always soluble, a cation from the always soluble list. All right, that was a good parade into Lab 11, dealing with buffers, dealing with Bronsted acids and bases. Way away. Oh wait, sorry, I'm scrolling back up. Okay, Susan, sorry, just saw your question about the chapter, or the new stuff material for the final. So as of right now, I'm finishing up the chapter 9 and chapter 10 stuff. That'll make it on the final. I don't know if there's going to be new stuff beyond that. Part of it depends upon how this kind of review process goes. But I do want to let you know that I will be posting this material either tonight or tomorrow morning. Depending upon when I finish it. All right, let's kind of take this moment. Oh, okay, Susan, sorry. That answer was not the answer to the question you just asked. I started scrolling up the thing and saw a question that you asked that I had missed a while ago. The question about how I knew to add a metal is based on the definition of a neutralization reaction. So neutralization reactions are defined as an acid, HA, plus a hydroxide base that has some metal cation, and it produces water and a salt. All right. So how I knew to do the metal is the reactant. On the reactant side, there's a metal hydroxide, which is the hydroxide with the metal cation, and then it produces a salt with that same metal cation. So, but for the record, you could pick any cation from the always soluble list, and it would work. So that's where that that metal came from. So I knew it could be like sodium, potassium, lithium, any one of those dudes. Just based on the definition. I mean, there could be others as well, but those are kind of the safe bets. Okay. All right. I'm thinking, because I floated this problem out there at the beginning of lecture, and then we moved on to do other things, but it's been sitting for a while. Let's circle back and work this problem. And it's actually, it kind of dovetails pretty well with what we've been talking about, because you can see we've got hydrofluoric acid, we've got calcium hydroxide. This problem, I didn't intend this. Sometimes things just work out nicely. This is a neutralization reaction, right? It is a reaction between an acid and, look at this, calcium hydroxide, a metal hydroxide base that produces water and an aqueous salt. So look at that. How cool is that? And the thing is, we know, so you'll notice, step number one, we have to balance this thing, right? That's what we got to do. And they don't tell us the salt, but we actually know what that salt is going to be made up of. That salt is going to be made up of the metal cation and A minus, right? A minus is fluoride. I need to color code this better. Okay, so A minus, whoops, did not mean to delete the little legs of my A there. Oh, give me 1 second, sorry. Photoshop is frozen. There we go. Okay, we're back. Notice that A minus is F, right? Fluoride, and the metal in the metal hydroxide is calcium. So the first step of this reaction, we need to write the balanced chemical equation so we can find our stoichiometric coefficient. And we have HA, not HA, HF plus calcium hydroxide, right? Calcium has a charge of +2, hydroxide is -1. Oh, yeah, fluoride. Yeah, well, oh, yes! Spot on. Calcium fluoride is that salt. Exactly, as we'll see in a minute. So we have HF plus calcium hydroxide producing H2O plus our salt. Now the metal in the salt, that's fine. The metal in the salt is calcium, and the A- in the salt is fluoride, so this will be CaF2, calcium fluoride. All right, and this is our balanced, or no, it's not our balanced chemical, it's not our balanced chemical equation, it's just our equation right now. We need to balance it to determine the stoichiometric coefficient of water. So we have hydrogen, fluorine, calcium, and oxygen in this reaction. Oops, sorry, calcium, not carbon. We have one hydrogen coming from HF on the reactant side and two hydrogens coming from calcium hydroxide, one fluoride, one calcium, and two oxygens on the reactant side. Moving over to the product side, there are two hydrogens, two fluorines, one calcium, one oxygen. So you always want to go with what's easiest to balance, and the easiest thing that jumps out to me here is fluorine, right? We have, for fluorine, we have one on the reactant side, two on the product side. We need two on the reactant side, so we multiply HF by 2. We also have to multiply hydrogen by 2. It changes our hydrogen count. So now we have 4. You may notice previously we had 2 hydrogen on the reactant side, 2 on the product side, 3 on the reactant side. They didn't go into each other evenly. But here we have 2, now we have 4 on our reactant side. 2 goes into 4 twice. So that tells me that we need two water molecules on our product side. This will actually balance both hydrogen and oxygen in one fell swoop. All right, so now everything's balanced. Our stoichiometric coefficient for water is 2. All right. So that is the... Yes! Susan, that is correct. Oops. Oh, man. Okay, so we have a balanced chemical equation. Now we're asked how many grams of aqueous salt were made. This is a weird kind of request. When you look at what we're given in this problem, we're given that we had, that we have a 75.0 milliliters of HF of the solution, and we had 42.0 milliliters of the calcium hydroxide solution. We're given the molarity here, 2.08 molar, and then we're asked how many grams. Well, the thing is, we know the molarity of calcium fluoride is 2.08 Yeah, totally. Oh, total. I'm tripping all over myself with the typing thing today. So here, let's look at this. We want to find the grams Ca of calcium fluoride, right? We're given the molarity of calcium fluoride. We know that molarity is equal to moles over liters. Now here's the thing. If we had moles of calcium fluoride, we could find grams, right? So we need two things. We need the molarity of calcium fluoride, which we have, and then we need the volume in liters. If we had the volume in liters of calcium fluoride, we could use this equation to find our moles, and then we could use stoichiometry to convert moles to grams. The question is, what is the volume of the solution? Well, it's going to be the volume of the two solutions we mix together to make it. That volume is going to be (117.0 milliliters) or 0.1170 liters. All right. Now that we know our volume, we can use the molarity to find our moles of calcium fluoride, and then we can use stoichiometry to get our grams. So we have 0.208 moles of CaF2 over liters times our volume in liters, 0.1170 liter, times moles of calcium fluoride in the denominator, and then grams of calcium fluoride in the numerator. Now, calcium, what, 40 point something. We were using it earlier. Yeah, 40.08. Fluorine, I think it's 19 on the nose. Yep. 19.00. And we have two of them here. So we got to multiply by 2. So 19 times 2 plus 40.08 comes out to be 78.08 grams in 1 mole. Now moles calcium fluoride cancel. Liters cancel with liters. So we have 0.208 times 0.1170 times 78.08. And this comes out to be, let's see, with 3 sig figs, 1.90 grams of our salt. All right. So that is part B. And now, Karenza, you said for part C, if we can determine the molarity of HF, and we totally can. We're going to need to hang on to this number right here as we move forward. So let's try to find the molarity of HF if it was the limiting reactant. Now, molarity is equal to moles over liters. Now, even though we don't have our volume in liters, we still have our volume, right? 1 milliliter is 10 to the negative third liters, so we can convert that volume and get there. The question is, we need to know how many moles of HF we have. And we don't know how many moles of HF we have, but we do know that we have 1.90 grams of calcium fluoride were produced. So we can do stoichiometry to take grams of calcium fluoride to moles of HF. First step, we want to cancel grams of calcium fluoride, and we calculated this molecular weight just a second ago on the previous slide. So grams of calcium fluoride cancel grams of calcium fluoride. Next, we want to convert from moles of calcium fluoride to moles of HF. 1 mole of calcium fluoride is for every 1 mole of calcium fluoride produced, sorry, tongue-tied, 2 moles of hydrofluoric acid react. So moles of calcium fluoride cancel moles of calcium fluoride. So we have 1.9 divided by 78.08 times 2 gives us 0.04, let's see, 3 sig figs, 487 moles of HF reactant. Now we can calculate our molarity. We have 0.0487 moles of HF. Putting that over the volume in liters, so that'll be 0.0750 liters. Let's see, 0.0487 divided by 0.0750 gives us a molarity, whoops, not in yellow please, 0.649 molar. Susan, you are on the money. That is exactly what a generic reaction between a Bronsted base and water would be. Totally. Well done. All right, so that is that giant problem that I wrote at the beginning of office hours. Okay, I'm gonna, yes. Awesome. I'm going to scroll up just to see what peeps were asking for. Just because I don't remember. Okay. So we've got some chapter 10 problems. I need to post those. 11, exam 3. Okay, Kate, sorry, I'm just now seeing your question. You're saying, I noticed for exam 3 that you got an answer of 200 milliliters, but you weren't able to answer in scientific notation with the correct sig figs, and perhaps your answer was off. Not sure how to proceed. Yes, one of the downsides to the numerical answers in what's it called? Canvas, the numerical answer problem, is that they don't accept scientific notation, which is why when I was writing the problems, I was purposefully making sure that none of them required scientific notation, so you could always like enter it with the right number of sig figs. Just because I was writing with that specific intention in mind doesn't mean that I didn't potentially make a mistake. So I'm making a note to myself to check your exam 3, because I suspect it was probably because your answer's off, because I remember writing problems and being like, okay, let's make sure that they don't need scientific notation. Check Kate 5's dilution. Exam 3 dilution. Okay, I will look into that just to make sure the mistake wasn't my own. So Kate, if you're listening, I will be looking into that. Okay, let's see. Okay, it was your number 11. That's actually super helpful. Let me write down that piece of info. Okay. All right. So there are some generic, some general questions about chapter 10, and what would be some good stuff to review. Yes. Yeah. You're number 11 on exam 3. Totally. And let me take a look. Yeah, we totally can. Let's see here. Okay. All right, where is that lab thing? It's over here. There we go. Susan, you said lab question number 3. Excuse me. I apologize for yawning. It is the mileage, not the company. My wife is a nurse at Kaiser, and her shifts start at she has to wake up at 5 to get to her shifts, and I get up with her, which is why I'm a little why I might seem a little beleaguered today. She worked yesterday, and she didn't work today, but I still got up at 5 because I have as you know, we have a final coming up, so lots of work to do. Okay, this was about soap. Based on the concentration for hand soap. There we go. All right, so we got hand soap. All right, Susan, is a great question. and I'm glad that you asked it. All right, so this is, nope. This is lab question, or sorry, lab 11, question 3. Oops. Okay, so in this problem, we have 0.5 liters of soap, and we have a pH of 10. .0, and then we're told to add half a liter of water. Oh. There we go. So that's our pH after half a liter of soap is added, and then we have .5 liters of soap plus half a liter of water. And here the pH is 9.65. Okay, so question 3 wants us to determine the concentration of hydronium and the concentration of hydroxide for both of these. All right. Now, to solve these problems, we're going to have to take a little, we're going to have to use our properties of logarithms again, just like we did before. So just to give us all a refresher, all right, so we used these earlier. I almost said we used these the other day. So here's the thing you want to remember. If you have 10 to the power of log x, this is just going to equal whatever is in your parentheses, right? This will just equal x. And you can take an equation make both sides exponents of 10 it's 10 to the 2 plus 2, and they'll still equal the same thing, right? It doesn't change the truth of the statement. They're both still true. We're going to use both of these because, take for example, we want to find or FID, I guess. We want to find the concentration of hydronium, and we're given, right, so this is the molarity, we're given the pH. So the pH of soap before water was added was 10.00. All right, now, anytime you're given a value that has an equation that goes along with it, you automatically want to write that equation. And pH is one of those things. pH equals -1 times the logarithm of the concentration of hydronium. And all of a sudden, we're seeing hearts for eyes, right? We want to find this. We're given the pH. We can do it with this equation, all right? The first step is we need to multiply both sides of this equation by -1. That way, the two negatives become a positive, and so we get the expression negative pH is equal to log times the concentration of hydronium. All right? Now we're at the place where we're going to make both sides exponents of 10. So we're going to do just like we did up here, 10 to the negative pH equals 10, oops, let me keep my color coordination going. You can see this equals 10 to the log of the concentration of hydronium. The reason why we're doing this is because of right here. All right, this will just equal the concentration of hydronium. So the concentration of hydronium equals 10 to the negative, and then our pH, right here, pH is 10. So concentration of hydronium will be 0.1234. You know what? I'm going to write it in scientific notation. It's going to be 1.00 times 10 to the negative 10 molar. And again, you don't need to worry about sig figs when you're dealing with problems with pH. Don't even stress about it. All right, so that is how you use the pH to find the concentration of hydronium, but that's only half the problem. All right, now that we know the concentration of hydronium, we need to find the concentration of hydroxide. So let's do that second part. You gotta find hydronium first though. So now let's find our concentration of hydroxide, and we're given the concentrate. Well, given the concentration of hydronium. We found the concentration of hydronium. Hydronium. We found this ourselves. All right, and you can do this using the equation for the water ionization constant, Kw. Kw is equal to the concentration of hydroxide times the concentration of hydronium. All right, and Kw, so to solve for hydroxide, you divide both sides by the concentration of hydronium. So we get an expression for the concentration of hydroxide is equal to Kw over the concentration of hydronium. Kw is 1.00 times 10 to the negative 14th. This is divided by 1.00 times 10 to the negative 10. Because that's what we solved for in the previous step of the problem. Now we can crunch our numbers. We'll get a molarity of hydroxide. That is 1.00 times 10 to the negative 4. All right, now I see there's been kind of a pileup of questions since I started working this problem. Again, this was, I think I got rid of it. Lab 11, question 3. So this is, I did this here to find the concentration of hydronium using the pH, and then once you have the concentration of hydronium, you use the Kw to find the concentration of hydroxide. See if you can give this a whirl. See if you can do this on your own. At the other pH, after we added 50 milliliters of water, the pH was 9.65. The steps are exactly the same. So see maybe if you can grind through that on your own, just because I want to see the couple other questions that we have piled up here. Let's see. Okay, Chen. Oh, hang on. Sorry, my screen's just went black. Okay, it's always slightly terrifying when your screen goes black in front of you. Okay, Jen, great question. So, let's see. I don't know. So I don't know exactly the problem you're referring to off the top of my head, but that doesn't mean I can't find it. If I had some more information. Do you remember? Because if I had a little bit more information about the problem, I might be able to find it. It was one line of info. Don't believe there's a question mark. I was just like info vomit. Okay, that might make it hard. Harder. See, would you mind, Kate, would you mind showing 50 mils? Just a numerical answer, okay. Let's see, it's still super vague. Just as it's about like a third of the questions in the problem banks are like that. If you knew what it was related to, like if there was gas stuff in it, if it was, you know, like a theoretical yield situation, then I would know where to look. Let's see. Sorry, Kate, I'm just reading your question just now. Whoa. No, that was not this problem. You're number 3. Okay, Jen, that might give me something to go on. Let me take a look. Based on the example. Okay. Gotcha. Let me see. Well, first, I'm on the message with message. Mission. I think message might be a combination of mission and message. I'm checking something out for Jen. Yeah, okay. Okay. So, Jen, does this sound familiar? Um, 44.0 liter metal cylinder. Stores a sample of gas at 23 degrees Celsius. Oh wait, hang on. Numerical answer. Okay, Jen, you were saying one line of info. Okay, so not this problem. Your number 4 was one line. Hang on. Okay. Yeah. Yeah. It's because your number 4 has one line, so it would go something like this. Just give me 1 second. Okay. So, determine the molarity of a solution of 78.0 milliliters of a solution diluted from 4.50 milliliters of 10.98 molar HI. Let's see. So, this is a dilution problem. So we have M1 V1 equals M2 V2. And so let's see. So we have, this is our V2 right here. We have our V1 and we have our M1 right here, and we're asked to find molarity, right, that final molarity. So it's going to start with dividing both sides by our final volume. M1 V1 over V2. So M1 is 10.98 molar. V1 is 4.50 mils. And V2 is 78.0 mils. Milliliters cancel, which is good because we are solving for a molarity. 10.98 times 4.5 divided by 78.0 gives us a molarity of 0.633 molar. We can only keep 3 sig figs because of our 2 volumes, actually. Each only have 3 sig figs. Let's see. Okay. Okay. Yep, totally. Jen, time crunch is real, and the testing environment is a different thing altogether. Okay, Kate, I hunted down a problem similar to that one. And actually, this is so I looked up the problem you were asking about on the tests, and let me just. Yep. Okay. So that problem is basic. It's the same type of problem that I worked earlier, the one that I wrote up at the beginning. Let me write a fresh one, and what I would suggest is rewatch how I solved that problem, and then use that method to attempt to solve this problem. So silver nitrate. Oh, sorry. Silver 1 nitrate, which is aqueous, reacts with aqueous sodium chloride, to produce silver 1 chloride which is a solid, and sodium nitrate, which is aqueous. Um, 14.5 mils of each solution is mixed. Together. To form a 0.640 molar solution of sodium nitrate. Okay, and then I'm going to ask for three things. One, I'm just going to say balance because that's what you got to do. Two, I'm going to ask for the grams of silver chloride. And then three, I'm going to ask if silver nitrate was the limiting reactant. What was the molarity of this solution? All right, so Kate, this is a recreation. This is a problem similar to the one you battled, but it's identical to the same type of problem that we did earlier. So I'm gonna say give this a crack on your own, but you can rewatch when I worked this later. All right, so let's see. Okay, where did we leave off? All right, part 7, for number 7, part T, in chapter 9, practice homework. Okay, hang on, let me get there. Number 7. Part D. Indicate whether or not the following reaction represents a combustion reaction. Okay, number 7, part D, chapter 9. Got it. Yes, okay, let me see. Okay. Okay, Kate, I'm not Kate, sorry. Carenza. I'm so glad you brought this up. So this is chapter 9, number 7, D. And this question is it a combustion reaction? All right, and a combustion reaction. A combustion reaction goes like this. You have a thing. Oops. You got a thing plus O2 making thing oxides. All right, so for example, CH4 plus O2 makes CO2, right, carbon dioxide, plus H2O. It's a hydrogen oxide. When you look at this problem, so part D, you have NH3, 4 ammonias plus 3 O2s. I'm sorry, I know this isn't balanced here. Producing 2 nitrogens plus 6 waters. This is not a combustion because this right here is not an oxide. So that's the reason this isn't a combustion. It's not just adding O2. All of your products have to be oxides along the way. So if you wanted to write the combustion reaction for ammonia, which is NH3, the products would need to be, let's see, probably, you'd have to have some nitrogen oxide like N2O4 plus H2O. So this is a combustion because you're adding oxygen. And then you've got oxide and oxide. Only oxides as the product of the reactions. Okay, so that was for number 8. Yep, totally. So here, let's number 8 is actually in the same ballpark, so this will be good. This is still chapter 9, number 8. All right, so part A. Is CuS plus O2 producing copper 2 oxide plus sulfur dioxide. B is Mg plus O2 produce 2 magnesium oxides. I don't know if you can hear that, but that's a baby playing out there. Next we have H2O plus CO2. Oh, sorry, plus not CO2, CO. Producing H2 and CO2. Let's see, A, B, C, D. Then we have C4H10O plus 6O2, producing CO2 and H2O. All right. Now here's the thing. You have to have oxygen as a reactant for combustion, right? Automatically got to happen. So the only one that's immediately disqualified based on having oxygen as a reactant is the first one. So this one's not combustion. Then, in addition to having oxygen as a reactant, your products have to be oxides. And this is an oxide. This is an oxide, right? It's sulfur dioxide and copper 2 oxide. This is magnesium oxide. That one's already disqualified. This is carbon dioxide. And water is dihydrogen monoxide. So these three, A, B, and D, are all combustions. And C is not. Let's see. Okay, currents. I'm seeing. Let's see. A. Yeah, so A is a combustion because the product is an iron oxide, but C is not a combustion. So that would be an error in the answers. Which specific problem? Oh, let's see. Part T. Oh, okay, sorry. I'm so sorry, Karenza. I thought you asked for part C, but I did, I thought you asked for part C, but you asked for part D. I'm so sorry. Let me do part D. All right. So let's see here. I just misread the question you were asking for. You want chapter 9, number 7, part D. Okay, part D is C plus CO2 producing 2CO. All right, and this one is not combustion. Because O2 is not a reactant. So that's the reason D isn't. Okay, awesome. Well done. Well done. Okay, let's see. Okay. So let's see. 22D, and then Parthana, I will jump to your questions next. But let's do chapter 9, number 22D. All right. Classify each of the following reactions as a redox reaction, a non-redox reaction, or a can't classify because of insufficient information. And D is a combustion reaction in which CO2 and H2O are products. Yeah. Oh, Prathana, I'm going to get yours in a second. Karenza just asked for number 22 ahead of you in the thing, and then you're next in line with number 28. Okay, so the question is this a combustion reaction? And the answer, well, we'll find out. Sorry, this is a combustion reaction. The question is it a redox reaction? So the combustion reaction is the combustion of something plus O2 producing CO2 and H2O. When you assign oxidation states, the oxidation state of oxygen on the reactant side is 0. Just because we're short on time, I'm not going to walk through step by step on how to assign oxidation states. You can rewatch the video from lecture. On the product side, the oxidation state of oxygen in both. Oh yeah, no, totally no worries. And I'll get to your number 28 in just a second. Is -2. Hydrogen has an oxidation state of positive 1 here. Carbon positive 4. So these are the oxidation states. Now you'll notice we have nothing to compare carbon or hydrogen to because we have no idea what this thing is. All right? We have no idea what the thing is. But we can compare the oxidation state of oxygen in O2 to the oxidation states in carbon dioxide and water. And you'll notice that it goes from 0 to -2. So oxygen has gained electrons, which means that it has been reduced. All right, it's gained electrons. Leo says GER, lose electrons oxidation, gained electrons reduction. It's impossible for something to gain electrons without them getting it from somewhere, right? If somebody bought, they have to be sold, right? Those electrons have to be sold to them. So the fact that we've identified one element gaining electrons means that some other element got oxidized. We don't know what that is. Could be carbon, could be hydrogen, but we know it happened. So because we identified one compound as having a change in its electrons, that means that yes, this is a redox reaction. All right, so that is number 22, part D. Let's go ahead and look at 28. Well, we turned there. Esther, the last day that grades are due to be submitted is August 10th. I will probably have them submitted before then, but and then they become available to you in your official transcript sometime later. So I don't know exactly when or how much later. I usually submit grades before, so it just depends on how long it takes student services to process all of the grades at the end of the semester. All right, Prathana, this is chapter 9, number 28. I think there's a part D. So here we're being asked to identify which substance is oxidized and which substance is reduced in each of the following redox reactions. And we're given a reaction. 3 molecules of sulfuric acid reacting with 2 molecules of nitric acid. Oh, we're making some. Wait, hang on. Yeah. Oh, sorry, this is not sulfuric. This is sulfurous. We're producing 2 molecules of NO, 1 molecule of H2O, and 3 molecules of sulfuric, H2SO4. Okay, so we're asked to identify what is oxidized, what is reduced. So we have a ton of oxidation states to assign. So Carenza, and this is true for all redox reactions, there's always one thing that's oxidized and one thing that's reduced. So 2 things will be changing, because one is gaining electrons and one is losing electrons. The redox reaction is always a process. It's always an exchange of electrons. And so if someone gains, they got to come from somewhere. Someone else has to lose. All right, so let's take sulfuric acid. So using the rules for assigning oxidation states, so whenever hydrogen is in a molecule, it's automatically +1, right? Unless it's the only nonmetal, then it's -1. Rule number 2 helps us out. Rule number 3 doesn't apply. We don't have any metals present. But the last rule will help us out. The more electronegative element takes its normal ionic charge. When you look at a periodic table, oxygen's higher than sulfur, so oxygen is more negative. It takes its normal ionic charge of -2. Hang on. Wrote these in the wrong layer. So we have +1 for hydrogen, -2 for oxygen, and then sulfur, we got to figure out. We know that 2 times the oxidation state of hydrogen plus the oxidation state of sulfur plus 3 times the oxidation state of oxygen will equal our total charge, which is 0. Hydrogen in this molecule has an oxidation state of +1. Sulfur we're trying to figure out. Oxygen has an oxidation state of -2. That all equals 0. So we have sulfur +2 -6 equals 0. So if sulfur -4 equals 0, that means that sulfur must have an oxidation state of +4. Did I hit the wrong one? Oh my gosh. Berthana, I'm so sorry. I wrote down 27D. Okay, hang on. Let's rectify this. Okay, 28D. Let's H2S. Sorry about that. Plus 2 nitric acids. So there's 3 of these guys reacting to make 3 sulfur atoms, 2 molecules of NO, and 4 molecules of water. Well, this one will be slightly easier, is the good news. Hydrogen's +1. All right. So now we can solve for sulfur because we know that 2 times the oxidation state of hydrogen plus sulfur is equal to our total charge, which is 0. So 2 times +1 plus sulfur is 0. If sulfur +2 is 0, then that means that sulfur has an oxidation state of -2. Let's look at nitric acid, HNO. Hydrogen will be +1. It's present with nonmetals. Oxygen, being more electronegative than nitrogen, will take its regular anionic charge. And now we can solve for nitrogen because H, oxidation state of hydrogen, plus the oxidation state of nitrogen, plus 3 times the oxidation state of oxygen equals 0. So we have a +1 plus nitrogen plus 3 sorry, plus 3 times -2 equals 0. So if nitrogen, we got nitrogen plus 1 minus 6 equals 0. That means that nitrogen minus 5 equals 0. So nitrogen will have an oxidation state of -5. Now looking at the products, sulfur 0. With nitrogen and 1 oxygen, oxygen's still more electronegative, so it'll be -2. This means nitrogen, to balance with it, is a +2. Hydrogen is +1 in water, and oxygen is -2 to balance. Oh, whoops. Sorry, let me rewrite those real quick. +2 minus 2, +1 minus 2. All right, now when you're looking for, they want us to identify which substance is oxidized and which is reduced. Oh, sorry, let me. There. When you're looking for who's oxidized, who's reduced, you got to look for changes in oxidation state. And one thing you'll notice is nitrogen starts at a +5 and ends at a +2. That's change for sure. Looking for something else that's changed in this reaction, another thing that jumps out to me is sulfur. Sulfur starts at a -2 and ends at a 0. That is an undeniable change. Now, when you look at these two, nitrogen starts at +5. It's my 2-year-old experimenting with his vocal cords. Nitrogen starts at +5, ends at +2. To go from +5 to -2, you had to gain electrons, right? You had to gain 3 negative charges. So we've gained electrons here. Sulfur starts at -2 and goes to 0. It has lost electrons. All right, because sulfur lost electrons, lose electrons oxidation, LEO. We say H2S is oxidized. Oxidized. And because nitrogen gained electrons, we say that HNO3 is reduced. So it all has to do with what gained electrons and what lost electrons. Okay, Susan, let me take a look at your question. Let's see, question 4. Let's see, how to find the number of molecules in a solution when using scientific notation. Okay. So, whoops. Okay, so Susan. Okay, so here's the deal. So, Lab 11, question 4. Let's see. Okay, so here's the deal. This is very similar to, it's actually, so they want you to find the concentration of hydronium and the molarity of hydroxide in chicken soup. All right, and this is, to do this, the same calculation as question 3, which I did earlier. So go back, take a look at that situation. That'll show you how to calculate the concentration for hydronium and hydroxide. All right. So remember, this is the same thing as molarity of hydronium. And we know molarity is equal to moles of hydronium over liters. All right? So if you take, and we know in this problem that we have the volume before the dilution is 0.5 liters, right? So take your concentration of hydronium before the dilution, I'm kind of jamming through this because I just saw the clock. I've got to run pick up my kids, so I'm trying to get at least a track laid down that you'll be able to follow. You take your molarity of hydronium before the dilution, so your moles of H3O plus over liters, which again you calculate the same way we did for number 3. And I ran through that already. Multiply this by your volume, 0.5 liters, so that liters cancel liters. Then you take your so we're trying to find the number of molecules, right? So then you use Avogadro's number, because you know 1 mole of hydronium ions have 6.022 times 10 to the 23rd molecules of hydronium in them. So then your moles of hydronium cancel and you're left with molecules. Esther, let me check real quick. And then I gotta bounce. Lab exercise 11. Oh, lab quiz 11. So let's see. 6, 7, 8, 9, 10. Yeah. Yes. So. So I think this will come as good news. Lab, just checked. Lab quiz 11 is 60% free response questions. So I got to jam out of here because I got to go pick up my kids. But thank you everybody for coming out. I hope it was a productive sesh, and I will see you all tomorrow. Take it easy.